We're now going to go directly into the first session of general speakers. So with this, we're moving into the Cloud Titan session. And so we have two of the very most well-known names in Cloud Titanship. That is to say, we have Microsoft Azure represented by David Maltz, and we have Google represented by Ines, Envid, and John Veizades. How did I do? Close? All right. So I'll invite David to start walking up to the stage, and there he is. David leads the network team at Azure, or something approximating that. And so I think we're going to hear a great couple of presentations here, and then we'll move into Q&A, so you can be writing down and capturing all those great questions you have for David, so that when he comes back up in about 40 minutes, you'll be able to pepper him with questions. Thanks a lot, and over to you, David.
OK, great. Thanks. Let's see.
Good job.
Is the clicker working?
Different clicker. Try the one with the red and green button.
This one. OK, great.
And only the forward button works.
No mistakes then. OK, so hi, I'm Dave Maltz. I lead the physical networking team at Microsoft Azure. We provide the connectivity for essentially all of Microsoft's online services from Azure, our public cloud hosting facility, through Bing, Bing.com, one of the world's largest search engines, Office 365, that whole suite of things that Microsoft runs. And to be clear, this is not my work I'm presenting. This is the work of the entire Azure networking team. So let me first talk a little bit about Azure. So Azure is a big cloud hosting platform, and it is getting bigger all the time. 85% of the Fortune 500 are using it. We get over 100,000 new customers every month. There are trillions of events going through our event hubs, 900 trillion requests per day going to our storage clusters. Perhaps interesting for this audience, 1 out of 3 of the VMs running in Azure are Linux VMs. And to tell you a little bit about the momentum and growth, a year ago, it was only 1 in 5. So we're seeing a great trend there as well. Now, to enable that kind of growth means we have to have lots of servers, really big data centers, hundreds of megawatts. So shown here is one colo, one place that we would put servers into a data center. And yes, that is 2 737s parked nose to tail in that colo space, and there's plenty of room left over. And to give you an idea of scale, this is one colo on a campus that might grow to have 16 of them. Right? And one of the reasons that we stopped putting more servers in a location is that just the risk of a 100-year flood taking out billions of dollars worth of assets eventually becomes so overwhelming, we think we should really move someplace else. Now, to enable this kind of scale, to enable this many servers, we need really big, really fast, highly available networks to connect all these things together. I am the physical networking team lead, so this is going to be kind of towards down on the bottom of the network stack. So here are some of the, what is the topology that we're going to use to connect together our physical routers? You've seen lots of papers on it, a CLO network, CLOS network, fat tree network. But essentially, we are going to use broad layers of switches. We are going to use broad layers of switches, starting with the top of rack switch, sitting on a bunch of servers, to then a broad layer of switches at the end of each row, another broad layer of switches at the scope of the data center building, and then another broad layer of switches at what we call our regional spine. And we've been iterating on this for about 10 years now, and major revisions every 6 months or so as we incorporate the learnings from that. So some of the nice properties of this is, well, it's scale out. It's active-active. So every switch is carrying traffic. If I need a data center to have more capacity, I want to move up to the next generation, I can just build a broader layer of switches. Right? This is the concepts of RAID for the network. I tend to build things in sets of 4. That's this rule of 4. So if I have a fire, if I have to do a maintenance, at worst, I lose about 25% of the network capacity. The rest of the capacity is there. And if we're running at average utilizations of 75% or so, I'm still OK. And so that becomes the target that we shoot for. Now, when I talk about broad, I do mean broad. Like this data center spine could have up to 128 switches in some facilities that are pretty big. Now, what that means is that if one of these switches were to lose its mind and go bad in some way, it's throwing all the packets away, it's corrupting some set of the packets going through it, it throws away some subsets of the packets that go through it, the impact on traffic is going to be less than 1%. And you're like, oh, that's great. You know what? That's not really hurting customers. except that a 1% packet loss is completely unacceptable because it totally screws the 99th percentile and 99.9th percentile latency of the applications running over it. And customers hate that. But it's 1%. It's 1 out of 128 switches that is having some minuscule kind of problem that only affects some of the traffic. How do we actually go find where the problem is? So one of the first things we did is we went and built what we call a ping mesh system. It's a pretty obvious idea. Logically, we have every server ping every other server, and we can't quite do that for scaling reasons, so we compute a reasonable partition and a minimal set of pings that need to be done in order to give us information about all paths, latency, and connectivity over all paths in our network. And this is great. The basic concept is in order to run a high-scale cloud computing network, we're going to have to use cloud-scale data mining techniques. We're going to take big data and use it to actually run our cloud. And the nice thing is you look at these ping mesh heat maps, which are basically showing the latency between a source rack and a destination rack, and lots of green is what you like to see. That's normal. If you see a big white missing data things, well, probably a pod set or a row is down. And when you see the big red cross, that means that anyone talking to these servers or these servers talking to anyone are seeing high latency, but the rest of the world seems like it's okay. So there's probably some problem in the uplinks or downlinks from that particular row. And when you see this, you're really unhappy because it means all the servers in a row can talk to each other just fine, but anyone who tries to talk between rows is having a bad day. There's probably something at the data center level. So from a visualization standpoint, ping mesh tells you when there's a problem and kind of roughly where in your data center it might be. Just to dig into that a little bit more, if this is a picture you see in heat map, well, it means the problem is sort of up here at these data center spines because, as I said before, traffic between servers in the row doesn't have to touch a switch having a problem, but traffic going between rows does, and that's why you see this sort of green blocky thing there. Okay? So ping mesh is pretty good for sort of seeing if there is a problem. Is there latency? However, it's not enough. So other things I could do to see if there's a problem in my network. I could look at the counters or the logs on switches and see if there's a syslog message that says, hi, I'm throwing away lots of packets right now. Or a discard counter that says lots of packets are being dropped. Unfortunately, many switches have what we call silent losses or gray failures. So they're throwing packets away or corrupting them, and there is no externally visible sign that the switch will tell you. We have ping mesh. So ping mesh, as I said, is really good at detecting is there a problem in the network, but it's really bad at telling us where the problem is. In that case I just showed, it could be telling us there's a problem in the data center spine, but that means that one of those 128 switches is having some problem. It doesn't help me find which one it is. Like Nick said, hey, traceroute, or the TCP versions of those, TCP ping, TCP spray, that essentially are going to do lots and lots of traceroutes and lots of TCP pings, explore all paths. So if we're in a reactive emergency setting and we need to diagnose something, yeah, launching lots of those packets could help us find where the problem is, but it's too high overhead on the switches and everything else to use that as a proactive service to find problems very, very quickly. And it turns out that these sort of direct probing methods that rely on end servers sending data, as typically done, won't detect dead switches or bad links unless they're carrying traffic, which means they're hurting my customers' traffic, and I want them out of the network as soon as possible. And so further, that means if the routing protocols take traffic away, I won't be able to see that there's a bad link there. And if I think a link has been fixed, I won't be able to test to see if it's really fixed until I put customer traffic back on it. And again, I don't want to put customer traffic on it until I know it's healthy. So these typical approaches don't work. So what's the solution? We've been using something called NetBouncer. Pretty easy idea and concept. We're basically going to use IP and IP encapsulation to create the effect of loose source routing. So what I can do is I can have a server, and I apologize, the figure's a little hard to read, that has multiple layers of IP headers on it. And I configure each of the switches to essentially do IP and IP decapsulation. So if I send an IP and IP packet to a switch, it's going to unwrap the outermost header, and then forward based on what's next in. So if there's a link between an L1 switch and a C1 switch that I want to test, I can take any server, pretty much anywhere in the world, and send a packet that will first forward to the L1 switch, where it'll be decapsulated, exposing the next inner header, which has a destination of the C1 switch. So the packet's going to flow across the link under test, where it gets decapsulated again, exposing the innermost header, which says essentially send it back to a logging server that'll see if it got through or not. Great. So with this pretty simple primitive, I can now go build a network bouncer service architecture, which essentially, like my ping mesh system, is going to arrange for the servers all over the world to split up the task of essentially probing all links in the network with traffic that I think is going to stimulate or simulate the kinds of things that could cause a switch problems. I can send big packets, I can send small packets, I can send packets of all sorts of different protocols. And I can target that exactly where I think that there's a problem. So if I think there's a problem that only shows up on if I send a high rate of packets, I can afford to do that and concentrate that target on a link that I think might be bad in order to rule it in or out. Okay, great. And we found that this system actually really does help how long it takes us to mitigate issues. So if I start with a ping mesh picture that, hey, there's probably something wrong there, but I don't know where in the network it is, I get an alert now that tells me, oh yeah, this is exactly the link that is dropping packets. Oh, and so this top curve here is what we call a scavenger drop rate. We have packets on our network that are best effort and packets that are scavenger. And the link on the scavenger traffic loss rate is quite high, and we're even getting some of the best effort drops periodically over time. But this makes it really clear this is where I need to go look in order to fix this problem. Okay. So combining ping mesh and NetBouncer gives us a good win-win. Right? Ping mesh can tell us, what is going to be the application's perception of latency coming from the network, help us detect if there's been an SLA violation of some kind. And then NetBouncer can help us very quickly zoom in on exactly where the problem is. Now, we found, interestingly, that running either of these systems in isolation doesn't work. The problem is that NetBouncer will sometimes report problems on links when really there isn't a systemic problem. There isn't something that the challenges on that link or that switch have not risen to the actionable level. They're not actually putting our SLAs at risk. And there would essentially be if I tried to act on every NetBouncer alert, there'd be too many. So we have to combine information between these two techniques to figure out what we actually need to go action to remediate. So talked a little bit in real big networks how we can actually go and find where problems are. Now you might be interested, okay, what tends to cause packet loss in big networks? Three main causes that we've seen of interest to here. One of them is switch firmware bugs. So as Nick was saying, a switch is basically a computer that's trying to program a bunch of ASICs connected to it over its PCIe bus and teach them how to forward packets at line speed. And lots of things can go wrong here. There can be logic problems in the switch firmware itself. There can be race conditions as they reach down and try and actually adjust registers and information that's in that switch ASIC. There can be resource exhaustion problems, either in the switch ASIC or in the general purpose computer that's running the business logic trying to drive the ASIC. So what are the solutions we're looking at here? I'm not going to talk much about it in this talk, but essentially we're trying to create open source software around the switch firmware space. And that way it can be battle hardened by Microsoft and also by everyone else who's participating in this community running data centers. There are two projects I just want to call out here. One of them we call SI, the Switch Abstraction Interface. So the goal here is to make anyone able to write firmware for any ASIC. We basically are abstracting away the details of the ASIC into a common abstraction layer that can be extended to support the unique capabilities of each ASIC, but provide some common ways of getting at all that and doing introspection to see what the capabilities of a particular switch is. Then there's Sonic, which is our firmware stack that we're using in our data centers, which essentially is then controlling these ASICs via the SI interface. And as I say, this is part of the OCP project, and there are lots of partners involved in this, and we welcome more. So all are welcome to join. Another big cause of packet loss that we've seen in our network is essentially parity errors. So usual cause here is alpha radiation from solder joints inside the chip package, corrupt the data on the switch ASICs. Now you'd think, what am I, Dave, you're talking about alpha radiation particles hitting my switch chip. How often can that actually happen? And it is a low probability event, but again, this is cloud scale, so anything that can go wrong will go wrong. So what are the solutions to this one? Well, we hammer on ASIC vendors to add error correcting codes to most all of their table memories. We work with the SDK vendors to actually get better at recovering from parity errors when they actually occur, detecting parity problems, detecting these big corruptions and recovering from them. And again, like Nick was saying, at an end-to-end level, we use NetBouncer and ping mesh to try and close that loop, to have higher level systems verify that the forwarding we're getting out of the network is the forwarding behavior that we expect. And when we detect problems with that, then we can go in and take action. And the action, we use a system called AutoNetPilot, I'll talk about briefly, to recover these. Another big cause of packet errors that we've seen is what we generally call lossy links. And this is because we have a very, very large fiber plant. And so there can be a dirty optical path from bad connections, what are called bend radius violations, optical transceiver failures. These are just some pictures coming out of our data center. So it turns out that fiber works because you keep the photons of light in the middle core of the fiber. And if you bend fiber too much, exceed the bend radius, the light leaks out of that active region and you get a lot of signal loss. So where's the bend radius violation? Well, turns out this one right here, that's a bend radius violation. Traffic over that link is going to have a higher packet error rate than traffic going in over these other fibers that meet their bend radius violations, most of the time. In this mess, there's the culprit right there. Someone was gathering up slack fiber and they wrapped it just a little bit too tightly. Okay? And of course, this stuff changes over time because as people are working in other parts of the fiber plant, they could pull or they could tug and create problems someplace distant from where they're actually working. The other thing, of course, happens is just dirty optics. This is a magnification, probably about 200x, of the optical active region of a fiber, and there's dirt on it. It requires very good craft, very good cleaning of the ends of fibers and optical transceivers before you mate them together to keep this from happening. When it does happen, well, we have systems, NetBouncer and what we call FCS, Frame Checksum Error Checker, that detect this issue. Again, that end-to-end model of what the network should be doing when they see behavior that doesn't match it, they localize where the problem is, and then a system called AutoNetPilot that goes in to remediate the problem. So let me tell you a little bit about how AutoNetPilot works when we're going in to fix these things. So it's based on the same network management system that we use for essentially doing all of our network management, from firmware upgrade through traffic engineering. We have something we call the network state service that sort of sits here at the middle layer. A bunch of network management applications run above it, and a bunch of hardware adaptation layers that know how to talk to all the heterogeneous complex goop in our physical network down below. So the idea is we have monitors that are talking to network devices or talking to servers that are doing probes on network devices that are observing what the current state of the network is. And that data gets published out to all the management applications who can subscribe to it. And if a management application detects something it doesn't like, for example, it sees a high rate of errors on a particular link, or it's starting to see a loss pattern that suggests that maybe a switch has lost its mind, it can propose that the link be shut off or that switch be rebooted. We have then a network checker that is looking at all the observed states and all the proposed states because there may be multiple management applications that know nothing about each other, all making different proposed values for the same entities in the network. And the checker basically determines which of these sets of proposed states would actually be safe. We don't want to turn off all the links to a switch because different management applications thought that something was differently wrong with each of them. So the checker's in charge of making sure that the target state that we want the network to go into is always going to, again, keep us in that healthy space. Right? So as Nick was saying, to use some of his words perhaps, this is making sure that we have a desired state configuration, and this target state, because it's now manifest and made visual, we can check to make sure that it actually matches the network designers and network architects' expectations about what should be happening in the network. To zoom in a little bit, in case you're curious concretely, you can read this while I talk in general terms. This is what happens for the FCS checker. This is the basic logic for the program that would correct the kinds of problems that I've been talking about. When the management application sees that there's a problem from the observed state, it's going to make a proposed state that say, hey, let's go turn that link off, let's go reload that switch. The checker is going to say, yeah, that's an okay thing to do, and accept it into the target state. At that point, the things that go and actually update our physical network are going to say, wait, there's a difference between the observed state and the desired target state, so I better now go in and configure this device or give it commands to do something, whether it's reload, turn off a link, drain traffic from itself, or whatnot. And then the thing that's not shown here and is a part of real network management is this system has to tie in with lots of other systems. One of the things I find fascinating about networking is it isn't directly connected to the real world. Not everything is virtual. Not everything is cloud. And if I have a problem with the link, I got to cut a ticket to a person who's physically on site, who's going to roll their card out to that spot, find the right fibers, and actually do a cleaning operation or a fix operation. And then when they've closed that ticket, then my automation can say, okay, is it actually safe? Did they really fix the problem? And then put that link back into service as they did. But there have to be all these interactions and interlocks tying into the real world to then enable the software-defined network abstractions on top to virtualize everything. So sort of in summary here, what I've walked you through is an example of how scale-out has really been the key to enabling low-cost, high-throughput networks, but it breeds low-rate failures throughout the entire network. And that means that if you want to run a reliable cloud, you have to have cloud-scale data analytics. You have to have a robust fault-tolerant management system that can drive automated responses. You have to be essentially closing the loop. You have to be looking at the observed behavior of your network, trying to see if it matches what you expect, and then taking remediation actions to make your network act the way you expect it to. In the cases here, I can report success. Over our years of doing this, we went from having a 1 in 1,000 packet error rate, packet loss rate on some links, which is enough to really wreck the 99 and 3/9 percentile latency of applications, to a world where every link has better than a 10 to the -5th packet error rate. And we stopped cranking the knob down there just because we stopped seeing more benefit in our applications. Probably as applications become more demanding, 6 months or a year from now, I'll need to go down another order of magnitude to 10 to the -6 or 10 to the -7. Right? But that's the kind of feedback loop that we're in as we build a network plant that will enable the most reliable networking for virtualization to then happen on top of. So I'm happy to take questions. I'm sorry.
But thank you very much,
He's in
David.
charge.
All right, well, I've got about half a page of questions that I've stored up, so we will have you back on stage in 20 minutes.
Okay.
Thank you. And so now we're going to welcome to the stage Ines, Envid, and John Veizades from Google. They are both product managers responsible for networking at Google. And they're just going to do a quick laptop swap because apparently Google's slides are so super secret they have to be projected from a special machine. So anyway, with that, having completely put you off your game, I'll hand it over and the clock is running. So thank you. There we go.
All right, so that was quick enough. Good afternoon, everyone. My name is Ines Envid. So I am product manager at Google. And it's really a privilege to be here today. By the way, we have a bunch of people from Google, so if you have the chance, don't speak to me, speak to them like in the breaks and so on. They're really some of the most accomplished engineers that we have in the team that build the infrastructure, so it's really worth spending some time with them. So I have 10 minutes. What I'm going to start doing is I'm going to waste my first minute, because as I was actually listening to Nick and to David, I realized, and I'm sure it's the same for a lot of the people here, is I've spent an outrageous amount of time throughout my career, which has been pretty long at this point, troubleshooting networks and trying to find problems in networks. And I just feel like when I was listening to them, I had this very depressing reflection about how I've spent those years in my life. And I think some of the, I'm really glad that some of the greatest brains are dedicated to solve these problems. And I think the future of the networks is really that we don't really have to build this exclusive club that we've built for networking, in which we're all super experts in protocols and in the state of each of the routers of the switches on the network to be actually able to debug the problem. So I think that's really a very ambitious goal, but I hope that we'll get there. So let me talk a little bit about what Google is doing in this space. And so in Google, we're really building like a huge ecosystem for enterprises to be able to get access to some of the capabilities that we've been enjoying for a while. And some of the challenges we have is how to actually make those capabilities public, make sure that we're providing the right level of control, policies, privacy for some of the users to get access to it. So we're building infrastructure as a service, platform as a service. We're working on very actively on containers. So we're exposing a lot of the APIs for machine learning, for big data processing. So those are some of the strengths at Google. And the network is important to the extent that actually support those capabilities. So it's really a supporting function, as I like to say it. The network is important when it is not there. So if it's working, if you really have the right latency, the right performance, throughput, you're having a right load balancing behavior, it's just there. And then that should be like the desired behavior. Obviously, it requires a lot of effort, brain, dedication to be able to build that to the scales in which the network is not relevant anymore. And this is really the goal that we are trying to accomplish. So what are the aspects that are important when we're exposing those capabilities to the users? Some of them are composability, so that you're able to be able to get functions that are allowing you to accomplish the use of your services, and you're able to compose them in a way that is so that you're able to achieve your goal, whether it is accessing to APIs, it is accessing your applications, your services. The other is reachability. As you are working on scaling your applications through, as your business grows, then it is really important that you have global reach, so that you're able to be driven by your applications and your services growth rather than your infrastructure capabilities. So our goal is to be able to extract all of that, so those capabilities are just there for the customer to use. And then, of course, latency and performance. We're building on top of our infrastructure, which is our production infrastructure that we've been running through years, in order to provide that level of scale to all the users. And on top of that, it is important to provide, of course, the privacy, the access through your private space, the capabilities for filtering, for absorbing those attacks. So there's a lot of security aspects that come with the model of multi-tenancy, in which you're actually exposing your infrastructure. And the capabilities can be great, but if you don't actually have the level of isolation and control to be able to have multi-tenant in your network and being able to feel like they're the only ones using that network, then all the efforts that I spoke about, they're really not relevant. So mapping that into what we're doing, so composability can be seen as network as a service. So then you need to provide the functions that are able to provide the capabilities in your services, load balancing for your web application, CDN for your content delivery, your streaming delivery, the VPN for your expansion of your hybrid network through your cloud infrastructure. So all those need to be in place, and it's to be able to use them coherently to provide your services. When it comes to reachability, it is important to us to offer a global scope, because that's what we've built our infrastructure on. This is where we have been building our services, and we believe that is something that it's really useful for others to use as well, so that when you're expanding your private space, you don't need to think about how to stitch your regions, and you're not on your own on sending that traffic across. It is really all taken care as part of our infrastructure. And in terms of performance, we're really proud of some of the achievements that we have had. We're, for instance, able to have a throughput of 14 gigabits per second across VMs that are sitting in the same zone. The latency intra-zone is around the 100 of milliseconds. And we're able to spin up thousands of VMs in minutes, which gives you great elasticity when it comes to spin up your services. And obviously, some of our services that we're building on top are all using these capabilities. The other thing that is really important is the capability of migrating VMs behind the scenes, so that we can actually perform our operational task, like upgrading kernel, without using any impact. So if there is a kernel upgrade, the instances will be behind the scenes, be moved to a different host so that the user is completely transparent to the user. So how do we provide all these network as functions as service? So there is a lot of vertical integration. There is a control plane and you can see it as an SDN stack that it is built in-house. So it has the capabilities of providing most of the functions distributed at the host, while being able to have a control that sees all those capabilities and is able to program and understand the state of those at any given point. Provides as well the level of isolation that is required to separate the customers and tenants in our network. So, and that goes integrated throughout all the physical connectivity, so that when we're integrating our controller, it really has access to all the hosts in the system where we're having our functions, whether are virtual networks or are VPN functions or are load balancing functions. They're all really integrated through the same control plane. Another important thing, I talked a little bit about live migration. The other important thing when it comes to networking is how do you actually isolate and give fairness to your users that are using shared bandwidth. And that requires very complex systems that kind of orchestrates and are able to integrate as clients in many parts of the network so that you can understand the utilization for your different users and are able to give them a fair amount of bandwidth where the bottlenecks are happening. And of course, as all of you know, that's not important where there are no problems, but when there are problems, you need to make sure you understand that in each of those bottlenecks, each of the users are getting their fair share. Reachability, when it comes to providing the reach to the extent that allows you to grow your applications or your services, again, we think it's really important that we are able to give a private connectivity that does not require any other kind of arrangements, so that it can be done within our Google infrastructure. So when we're spanning our virtual private network, which is the private domain where it's kind of a sandbox for each of the users to spin up their applications, you have the capabilities of choosing the regions where you want your services to live, but they're all privately connected. And they can be segmented by regions in terms of CIDR allocation and so on, but the connectivity is natively private across all the regions. The other thing we've recently done is giving the capability of expanding CIDR ranges on the fly so that you can have services running, expand your CIDR if you have a need for expanding your service and so on. So it is pretty flexible that way. So just to finish, all these capabilities that I talk about that get exposed, obviously they have a lot of infrastructure behind, which is the same infrastructure that is being built across the year and that it is used for the rest of the Google scale services. There is a dedicated internal backbone, which is called what we call V4, which has terabits of capacity. There is the backbone where we're peering with the rest of the world, and it's kind of running in parallel. And finally, we have like around more than 100 points of presence where we're pairing with external parts. So all these are kind of the infrastructure that is underlying the capabilities that I talk about. And having said that, I hand over to John, who's going to talk about security.
So that's our network, and you can't talk about a network without security. And in an enterprise, you start thinking of security in a sort of this kind of onion actually me. Thank you. So if you look at it, you think about security in this onion mode, right? Where you're thinking about data security, application, host, network, and finally your facility security. And there's a large number of people that are involved in dealing with this level of security. But as you move to the cloud, you still have to think about all of this, but you're no longer thinking of it as an enterprise because you've taken that function and you've handed it off to a cloud provider. You handed it off to an Azure, an AWS, or a Google. So we have to think about it. And we take a long time thinking about this. We've developed a stack view of the things that we need to think about security. And if you look at this, it actually is a very complex set of security aspects. So many of us, we're all thinking about network security, but really network security is just one thing. If you don't do all the other aspects of security, network security just doesn't give you a whole lot. And if you look at the things that we're looking at specifically from a security standpoint, we think about platform security. So it's trusted boot, it's actually trusting the OS, the applications that are running on that OS, and you can bringing up your network in a way that's trustworthy. Has to start with the platform level of security. Then you also think about policy, who can do what to whom when. And that's another aspect that we have to think about when we build the infrastructure and expose it out to customers so they can make those decisions. Because those decisions are based on enterprise level controls. So exposing all that level of security and policy out to the customer. Finally, we think about data protection. So data encryption. All your data at rest needs to be encrypted. And when you take your data from your enterprise data center and move it to a cloud data center, you want to have at least that level of security you have in your private data center. Most private data centers don't think of data at rest security. Google does think of data at rest security because we realize that's the next level that you have to take your security to. In a data center like an Azure or a Google data center, we have hundreds of thousands of disks. And when you get to that level, they fail on a regular basis. When we're doing that with your data, we have to be concerned about what happens to that infrastructure. How do you get rid of it when it finally fails? And if you can't accurately delete it off of a hard disk, what do? We have robots that shred disks when they can't be used. So all that comes out of the back end is a bunch of metal shavings. And then finally, compliance and audit, so that when you're thinking about PCI workloads or HIPAA workloads, that you have the same level of security that you're audited to on your data center moves that level of security and auditability to the cloud. So all important aspects of building security in the cloud. So in closing, because I think we're just about out of time, it's a holistic, security is a holistic approach. You have to think about how you do it from the top down and from the bottom up. What Ines talked about, our global network, is an asset that lets you build networks in the cloud so you don't have to build them physically yourself. So suddenly you take out the aspect of building a global WAN because your cloud provider is providing you that global WAN. And then standards, and finally, hopefully, industry-leading infrastructure and scale and performance. That's all I had to say. Thank you very much.
3 speakers back on stage, and we'll start the Q&A.
Sorry about that.
All right, I'll separate myself out a little bit here. And do we have microphones out in the room? Are there people running microphones if we need them? So we are going to start taking questions from the audience in just a second. But so my first question I have to ask David is, what were those 737s doing in your colo? Actually, there was one question I thought I'd ask all of you to answer, and This is just an example of the kind of what I hope will happen is that there seems to be obviously a lot of commonality between your two talks. And so I thought, having just heard Nick talk about the wonders of programmable hardware as he envisaged, it may happen in the future. You both sort of talked about what you do today with the hardware that you have. Do you see a need for more programmable hardware in the future, more programmable switching hardware? And if you could get it, what would you do with it? So you can take it in whatever order you like.
Do you understand?
So yeah, absolutely, right? I don't think there's any other answer to that question. And what would you do with it? A lot of what we said earlier is really about thinking about how you do packet processing. There's a theme that's been going through all these presentations about if you could have truly programmable hardware, what would you do? And a lot of it is making it easier for us to go and build generic solutions to common problems rather than having to go to a vendor community and say, hey, have you gotten this level of functionality done? We think about things that we can't implement because the underlying hardware won't let us to do it. So.
I think the other really important aspect of it, and I think as well as we're talking about the future of the networks, is like a lot of those functions as well, they get more and more distributed. So when you're really moving some of that intelligence away from the centralized routers, centralized switches, you're moving those to the host, then you're obviously talking about how to program those on the fly. So you really need a lot of flexibility, which is paired with high performance. And I think all the new generation of software is really, of hardware is enabling that architecture. But I truly believe that that's really the future of the networks, is really moving that intelligence in a distributed manner, and you need a lot of flexibility for that.
To put some spice into the debate, I'll be a little contrarian.
Okay.
So, as you heard in my talk, one of the things I'm very concerned about is that it's closing the loop. It's being able to validate that the network is doing what we expect it to do. And so I think programmability is potentially a blessing and a curse, because it provides another set of things. Because it's programmable, it means it's going to change as developers release new things that I actually have to include in my debugging model. And I'd like a very simple, robust model of the switch itself, so that then as I'm trying to essentially reverse engineer in my analysis what's happening, I don't sort of have to worry too much about there actually being a bug or new sort of complex logic that's creating new behaviors and responsible for the data that I'm seeing out. And so I think there is some tension there. Now, the ability to use programmability on the switch hardware to get more monitoring, to get more visibility, that is pure goodness. But in the same way, Nick was saying, if we identify the right architecture for the switch chip itself, piece is right, if that's the right architecture, then I can sort of use that as the simple substrate underneath everything. If we could figure out just some set of encapsulations, those same primitives that we want from the hardware devices themselves, then I might not need a fully flexible data path. I mean, yes, it's true that there are lots and lots of encapsulation protocols out there, but in reality, they're all mostly interchangeable. I just need one. I need one to be supported well. I don't really care if it's VXLAN or NVGRE or GRE or IP and IP, right? There's some set of primitives that I want from the switch. And getting those simple and robust and easily described and modeled for the higher level analysis, I think gets us a long way. And then monitoring is pure goodness.
Yeah, I mean, it a little bit gets back to the point that Ken made during the quick Q&A for Nick's talk, I think, which is like programmability is all well and good, but the question is, to whom do you expose the programmability? Maybe you expose it to the monitoring team, but not to the application developers, for example. Excellent. Well, let's see if there's any life in the audience. So who wants to ask the first question?
Was that
okay, we'll hear from Ashok. Don't you guys talk to each other?
Never.
I don't know who he is. Who are you?
I think they don't really want to know who I am, because I don't know them. So your the model checker, the thing that moved from the proposed model to the target model, was an interesting concept. And one end of these things are based on heuristics, such as I don't want to turn down more than X amount of the network because I feel like it. The other end of it is based on a provably correct model of the network. So my question is, how far along that are you? And especially, how does that work with reboots, which are more like edge-triggered interrupts as opposed to level-triggered ones, which are interfaces which are up or down, seem to play a special havoc with heuristic-based systems. I'm curious how it affects you.
So I do very much see it as a continuum, and it's one of these things that we continue to iterate and evolve on over time. I would say today we're very much at the heuristic level, or maybe a little better than heuristics, because again, we designed our network architecture so that it would be easy to write some of these validation primitives. So one of the things we like about, ECMP, oblivious traffic engineering, because it means the utilization on all the links in certain groups should be roughly the same. And when it's not, it means we do have big flows or something unexpected is happening there. It pushes us towards things like, hey, could I do per packet round robin to get even smoother traffic equalization across paths? So we sort of designed the network so that it was easy to write these validation logics on it. And our goal is to then, sort of increase the level of verification and validation. Coming out of some of the papers we've published, Batfish, things like that, you've seen some of our efforts there to up the game.
All right, I saw at least one more hand. Oh, maybe right at the back there.
Hi, Rob Shore with Big Switch Network. So one of my favorite things to track over time is what I think of as the still ongoing battle between RISC and CISC. And so if you think about like what the packet processors look like right now, those are extreme CISC instruction sets. And there's certainly a movement, and I'm very much supportive of making them a little bit more RISC-like. But if you look at how x86 is evolving, it's certainly become a little bit more RISC, but we're still inserting these very high complexity instruction sets, the ANS, NI, the VT instructions, some of the MMU things. What are the low-level primitives that are still very complicated that you would like to see exist in the network that don't exist now, that would make your lives easier?
Wow, that's a good question.
Good question means you haven't thought about it. Apologies.
Going back to the earlier presentation, really, the arbitrary composability of packets would really help. In other words, what are those 11 operations? Add stuff to the beginning and the end. Tweak some bits inside. Do a mapping of some sort from one IP address to a table, et cetera. So those types of primitives make it easier to build networking infrastructure. I think we still have to see it to make a decision on what we would do with it once we see it. I think that's always been the real challenge, is seeing something from vendors that makes sense.
I think that's it's really a hard question. I think I tend to think that the most challenges that we're hitting today in order to provide easier models to customers are hitting things like an agreement across different platform, multi-cloud, hybrid on orchestration, and how you're actually able to apply the same functions consistently with the same type of constructs. And I'm not sure that really belongs to the chipsets itself, but it's more like an industry agreement on how we actually are able to compose those functions and make it easier for the user. And some of those things are not even technical aspects. They're more about how we are actually able to bring all of us together a model that we feel comfortable with, and then we feel that it's a win-win for all of us to actually expose. And I think until we don't really solve that problem seriously, I think some of the other aspects are a little bit not relevant just yet, because I don't feel we're hitting some of the bottlenecks there.
David, did you want to?
Yeah, I would say most of my wish lists are around in data plane aggregation of counters, queue lengths, high watermarks, low watermarks, and the ability to then, say, put that into scalable monitoring systems, which either means ability to stream that data off of the ASICs back towards geographically distributed collectors, or good support for packet scratchpad space, so that the data can actually be carried along with the packet as it flows through. And those are the kinds of things that I ask vendors for.
Cool. Let's maybe go back to, I know Ken had his hand up for a while.
Yeah.
So Dave, you guys are doing so much great stuff with open source and Psi and Sonic. Have you considered open sourcing ping mesh, NetBouncer, AutoNet Pilot.
So
It's your competitive differentiation, right?
yeah, so some of these things are competitive advantages. And so to build a cloud scale data center actually requires making very large investments in the systems to manage that. And since we are in the cloud hosting business, both as a product that we sell as well as to support our first-class services, our first-party services, we probably won't be giving some of that software away. Now, things like Sonic and Psi, they really are open source efforts. Why? Because those are things where we believe in the open source method, that we can actually make that software more robust by having more eyes on it. And that the enterprise segment may want to battle test some sets of features that I don't particularly need. I will want to battle test the stuff that I need in my data centers, and that combined set of code base then becomes a good library that other people can draw from when they want to compose their needs for their firmware.
Yep, another question right there.
Thanks, Ron Parker from Firm Networks. David, you talked about 3 classes of errors that you go after in your network. And I noticed that one of them wasn't loop detection and prevention. Are we just completely past that now? Is that a problem that we don't worry about anymore?
Yeah, haven't had one of those in a long time. I mean, the problems I have, we do use BGP as an IGP inside of our data centers. You've given talks at NANOG on sort of our routing architecture. And so we've had horrible nights where BGP is flapping all over the place. I have seen BGP ring across entire data centers. Luckily, those are years behind us now too, but looping packets isn't something we do very often.
I was curious, David, that you talked a lot about sort of how you troubleshoot what's going on with your network, and there was a little bit of talk there about how you, when you go through that sort of planning process, you say, okay, I'm going to come in and shut down this switch or shut down this link or something. So there seemed to be a sense that most of the time, in an ideal situation, your network's kind of in a steady state with you're not going and doing moves, adds, and changes all the time. But then when you do need to do them, it's typically for maintenance or troubleshooting type reasons. So do today's networking equipment does today's networking equipment give you the necessary APIs to make that a straightforward process? Because traditionally that's kind of a nightmare to sort of manage all the different boxes and say, oh, I want this one to shut down this link, and to have some special secret CLI command to do that. So how's that part of the thing going?
It is a challenge for us today. We run a heterogeneous network with devices from many different vendors and manufacturers. We do that as a way of honestly getting better pricing. We run an RFP process. We say, look, if your switch can meet the following kinds of functionality, then we will qualify it, and if your bid comes in low, then we will use it in our network. And that means that our network management architecture needs to have that hardware adaptation layer that can talk to each of the various devices. And so we're very interested in all the work to try and unify protocols for talking to network devices, open flow, extensions to BGP, netconfig. And we don't know which one's going to win. And so we are providing essentially a framework for supporting all of them. And then with Sonic, again, that gives us yet another way of essentially integrating switches directly into our network management systems.
Mm-hmm. Cool. More questions from the floor? All right, maybe people are starting to lose energy here. Well, I've got more questions. Oh, actually, there's one right there. Yeah, Mr. Skarupa.
Question on Sonic. We've heard some discussion about it a while back, and then a bit more from you now. How broadly is Sonic deployed?
So we have several hundred switches in one of our data centers that are fully running Sonic. So we have 100,000+ servers that are dependent on Sonic for the network connectivity, and we are growing that out pretty rapidly. In the Sonic community, as you know, we're switching between V1 and V2, and so we're doing a pause on deployment while we're consolidating behind the V2 push, but then we're going to start rolling out again aggressively with V2.
Thank you.
One more question. So if you think about how the internet evolved, you started with small networks in universities, and then slowly they've been merged together, they start to communicate with each other. We have Google Computing Engine, we have AWS.
Sorry, can you hold the
Azure.
microphone a bit closer? Yeah, thanks.
We have Azure. Do you think, wouldn't it be normal for you guys to think how you can make these networks interoperate at the workload level point of view instead of having proprietary solutions?
Yeah.
So I think they, for some amount of interoperate, they do that today. I mean, we actually, peer with Azure, we peer with AWS. You can run a workload. Now, granted, moving a workload from a Google data center into an Azure data center might be a little bit difficult. But from a network layer, you could run your database tier in Azure and your compute tier in Google, and you'd still be happy.
Yeah.
Maybe.
I mean, I would say that there are companies who are making it their business model to help enterprises onboard to multiple clouds.
I believe I've met one of those companies.
And I think that it is certainly the case that you can sort of pick and choose from the services that you like. If you like Google Storage and Azure's Event Hub, you can combine that back together. And that we are kind of in a world sort of like internet ISPs are, in that there are places where we cooperate, there are places where we compete. In the ISP world, we've been able to come to agreement on some kinds of mutual traffic engineering, and there are other kinds of traffic engineering and costs that remain quite difficult to achieve across different ISPs.
I think the industry has done like a decent job in interoperability efforts for a long time at the data plane level. So I think a lot of those problems have been solved, through the standards. And so obviously, as the kind of frameworks and vendors and capabilities are evolving, I think, again, going back a little bit to, I think the main challenges that we need to tackle as an industry is the standardization of the construct that we're using to express the logic of our functions. And those are kind of the orchestration layers and some of the companies, of course, that building on top of our APIs, because we are actually not able to come up with standardized solutions at that level. And to be honest, so containers and orchestrations like Mesosphere and Kubernetes are trying to solve that problem to some extent. And I think those are the capabilities that customers are appreciating in some of those solutions, because they kind of build a control plane on top of the platforms that are existing. And then it's, of course, all the templatized models that other companies are building, so that you can use the same template to actually apply the logic across different APIs. I think those are the challenges that we're having today, and I think that's where a lot of the work needs to be done in order to make it seamless for the user. At the end of the day, even if we're peering with Azure, yeah, sure, we can send packets across, but when you really want to have like more intelligence above, it is really difficult to express with the same constructs that logic.
It's the next level of abstraction, is what we're headed for, right? We have really good network abstraction layers, and the next is these application abstraction layers that let you do workloads that you're interested in, not just the networking aspects of it.
Yeah, I wanted to pick up on that topic of abstractions. Actually, I do remember that talk that Nick referred to from Scott Schenker 5 years ago. I think that was pretty much the day I decided it was time to go and join a different company and work on software-defined networking. When you, John, put up your slide that had all the things you do for security, it gave me a bit of a queasy feeling compared to the sort of the nice clean abstractions of networking that Nick was talking about.
Security is never
there's
no clean abstraction layer on security.
It was like there were 400 things that you need to worry about and no organizing principle.
Correct.
So that's where we are for security, right? Just want to make sure that I've got that right.
And the thing is, security is really talking about the threat model, right? And the issue with threat models is that we're all really bright people in this room, and we can think of threat models that we contemplate them and say, yeah, that's a problem. There are an equally set of bright people outside of this room and in other parts of the world that are thinking exactly the same way. So security is, everyone says it's an arms race. It truly is an arms race, and there is no abstraction layer to it because it really is a very abstract problem, and there's no one way to attack it.
I mean, one thing I will say from my own experience is we are increasingly finding when we talk to customers who are now mixing their different clouds together and maybe having some amount of stuff they run on their own data centers and other things on Google and other on Amazon and others on Azure, that certainly would like to see sort of basic things like, if I could just say, like ACL configuration be the same in all places. So it's sort of like at the lowest levels, maybe there's some things that we understand, and then again, I don't think there's any sort of rush towards standardization there, but at least that is the opportunity. I think.
From a policy, you think about security as lots of things. One of them, the more enterprise portion of security, is really about policy. And I think there's probably abstraction layers around policy that could be developed in a standard way.
Yeah,
but,
I mean,
a lot of the other stuff is around the edges.
It does seem like there's room for new common abstractions here that would allow unification of some of this. Now, honestly, even if you want to think about sort of the layers of the cake, there's the management layer, then security layer, and then above that, the political layer is the compliance layer. Mm-hmm. And so even once you have a system that is secure, each of the various compliance audits that your system will need to pass and that your customers need to pass will typically require a different set of evidence gathered in a different way to meet that. And so to some extent, even if we manage to get a common policy language together, there'll still be a myriad of different objectives and reporting and auditing needed on top of that to make all the different compliance organizations in the world
each one
content.
of those is different.
And each of them is different today.
Are there other questions from the floor? Yeah.
Hi, this is Louis from Facebook. So this is a question for Google. Google traditionally has been very open in the open software space, but on the hardware infra side has been a bit more conservative and secretive. So I was wondering if there is a chance to see more of Google in that kind of infrastructure space, and in hardware designs and the software running on top of that in particular. Thanks.
Oh, that's a great question. That's one of those questions that I can actually say is above my pay grade. What we do is an asset to the company, just like what we talked about with Azure talked about. These things are things that help us run our business. So it's really difficult to public open source things that are critical infrastructure and how we run our business.
Although, I mean, you've been very open about the architecture of the physical fabrics at Google, but I guess the question was more about sort of open sourcing the software. So the software on the switches, you view that as a competitive differentiator?
Absolutely.
Yeah.
Absolutely.
As you said, there's been and recently more so, a lot of papers on actually the architecture to a great level of detail. So there was recently the papers on how we actually load balance throughout our architecture with what we call the MacLabs. There's been some white papers about bandwidth enforcement, so how do we actually do fairness across different users, across throughout our network and so on. So it's a great level of detail. When it comes to open sourcing, I think it's been more focused on protocols than really design practice themselves. So there's been, of course, all the efforts around gRPC, and when it comes to the implementation itself, that's where it really it's a little bit more close and proprietary. But
what may turn out to be our last question as we run down the clock here, but I think you both groups gave a pretty good view that things are going pretty well. You're sort of happy with performance, happy with reliability. What do you see as the sort of the big challenges that you need to deal with in the next sort of 1 to 2 years? What's not perfect relative to the nice sort of rosy pictures we saw?
Well,
where are the engineers there?
I think one of the on the networking side specifically, I don't think everyone is happy with latency. Mm-hmm. And I think what we're starting to see as cloud becomes a standard way of doing deployments, you start getting deployments everywhere. And when you start getting deployments everywhere, not everyone gets 10 milliseconds of latency. There are places in the world that you have hundreds of milliseconds of latency, and applications don't behave the same way when you do that, and end users want them to. So I think it's the ubiquity of compute, I think, is the next big challenge that would be great to solve in the next couple of years. And it's not just for North America. It's really ubiquity of compute globally, so you can think about things like Pokemon Go, and you have a great experience in Nairobi, the same experience that you have walking down the street in Las Vegas. So that, if you think about the nirvana, that would be, Pokemon Go works great regardless of where you're at.
So I feel like I just walked into an episode of Silicon Valley, right? It's changing the world through Pokemon Go in Nairobi.
Yeah.
David, you want to take the what's your sort of set of things you really want to fix in the next couple of years?
Okay, I agree that the sort of geolocation of compute is a challenge, and I think that to some extent the rapid growth of all cloud hosting platforms is going to fix that. But one of the challenges that I'm really interested in is we collect tremendous amounts of information about what's happening in the network, which we then use to debug and diagnose. And customers who are trying to bring up their applications are asking themselves the same kinds of questions that we ask when we debug our applications. Like, okay, well, what's going on? Am I getting the requests per second that I thought? Is it the big packets are slow or the small packets are slow? And so finding ways that we can take the data that we are collecting and partition it so that customers can see only the data that is relevant to their deployments, but giving them very deep insights into the performance and behavior of their applications so that they can tune them to get the latency and behavior that they want. That's an area that we're putting a bunch of energy into, and we're starting to see results.
Mm-hmm. Cool. Mr. Ward.
So what's interesting with those answers in the presentations that you gave, and it's very impressive to have a couple 737s in a data center and describe hundreds of megawatts. And then the problem being latency and the global ubiquity of compute. Many of your suppliers are working on solving the speed of light problem, but nonetheless, we're still a few years away of doing that. But anyways, I want to switch away from my comments just now and ask, is part of the designs that you see over the next couple of years towards power? And in particular, the requirements, hundreds of megawatts around the globe and even in North America, is a very challenging problem. And whether it's networking, storage, or compute, we've talked about one aspect of building chips and that Moore's Law potentially can solve some of our problems. But as we approach Moore's Law and keep doubling and doubling and doubling, pretty much the same amount of power you're using to fling packets just on the networking side, which is a relatively small percentage potentially of all the power that you use in those data centers, is simply going to leakage and is a huge problem. And there's a number of technologies relatively on the horizon that could solve that I/O problem, could solve these problems, and potentially get us away from building the next, instead of 300 megawatt data center, a 500 megawatt data center, an 800 megawatt data center, which it appears the industry is currently on the trajectory of a never-ending larger multi-hundred megawatt data center. And whether or not that becomes one of the biggest problems that we're all concerned with as an industry.
Certainly, having good power utility efficiency is critical for having low cost of goods. And so one of the ways that our companies do compete is what's the price of a VM compute hour? Right. And because power consumption is a cost of that, we're very strongly incented to find ways to very efficiently use power. I sit on a lot of program committees for networking research, and I see a lot of papers about how people are going to tune down the SerDes or something to save half a watt here or there. I'll admit, I don't think networking is the place where the big wins are going to come from, because the fraction of power consumed by the network is so small. And again, I think it's worth keeping the network simple and highly available and not adding a lot of dynamics there to try and save power. But in the data center physical plants, there's a 0.01 change in the PUE, power utility efficiency of a plant, turns into significant power consumption differences at these sizes. And there's a lot of work in server architecture and in how compute jobs are placed across the data center, which actually then in turn increases demand on the network to take those physically distributed servers and make them look like they're still one fungible pool. That's probably where the biggest improvements in power are going to come from.
If you don't mind, just a comment back on that, just one piece, which is that when you take a look at the overall network design that you showed with the application potentially parsing a packet, a virtual switch, virtual router parsing the packet, a NIC parsing the packet, a top-of-rack switch parsing the packet, a spine, another potential top-of-rack switch going out to a DCI, that's a whole lot of hops that are really not manipulating that packet, yet looking into the guts of it for one particular reason or another, counting or otherwise. It seems that overall, if we were trying to look at a different data center design at cloud scale, trying to optimize all of those hops, all of those paths, all of those inspections might be one place to do it, and whether or not you're investigating those.
Well, I think what you're going to is the efficiencies of moving data through your network and the compute cycles that take, every compute cycle is power, right? So if you can move data through your network more efficiently, you have great power utilization gains. I think the free market is actually, between exactly what you said. It's how much you buy per compute hour, what's the cost. Those things are driving us to do interesting and novel things in our data centers. And why do we have these huge data centers? Why do we have special purpose hardware, data centers that are custom designed by, engineers? They're not your average data center, put it that way. And it goes to how efficient can you get?
Yeah, I guess the quick Amdahl's law argument here is that if I look at that rack of servers, that rack of servers has got 20 to 40 servers in it, each of which are drawing, call it 300 watts, and one top rack switch, which draws 300-ish watts. And so and most of the power consumption is actually in those top rack switches because they outnumber, they're the most plentiful by far. So network power draw in watts is essentially 1/20th to 1/40th of the draw of the servers. And so even if I move the needle in a really big way on the network, I haven't actually changed the power I need to deliver into that space very much.
So we are slightly past our finishing time here, so I'm going to ask you to thank the speakers once again.
Thank you.
Thank you.